Alright, whoops, ran a bit of battery on my video. I'm going to go ahead and fill in the rest of this chart. So you've got tuberculosis or not tuberculosis. So most people do not have tuberculosis. And then you get tested. If you have tuberculosis, you get detected 95% of the time. If you have tuberculosis and you do not get detected, that's 5% of the time. That sucks because these people think that they don't have tuberculosis. And we have, let's see here, people that do not have tuberculosis get detected as having tuberculosis 0.2% of the time, that's unfortunate for these people because they're having all that stress. And then, anyway, to get this tuberculosis and being detected, you have a 95% chance. The entire population has a 95%, sorry, not 95% chance, 9.5% chance, and so forth and so on. And when you add these up, you get 1. So now we can use these to help answer the question. The question is, suppose if one of these persons is selected at random is diagnosed as having tuberculosis. So that's the condition. The condition is that they have tuberculosis. So the probability, given they have tuberculosis, what is the probability actually has tuberculosis? Okay. So this is not on our chart. We have diagnosed given tuberculosis, but we do not have tuberculosis given diagnosed. So let's work through the formula for this. You do probability of tuberculosis and diagnosed divided by the probability of diagnosed. So for us, this can be found right here, 0.0950. And the probability diagnosed, so there's a couple ways to end up being that you can have tuberculosis and be diagnosed, or you cannot have tuberculosis and be diagnosed. So actually we have to add up these probabilities because these both end in a diagnosis. So we got to add up like that. And then that ends up, when you put that in your calculator, ends up being that right there. This would be interesting with COVID. I should redo this problem. COVID. Alright, example 4. So pause, do it yourself, see what you come up with. So among 180 professors, 135 hold PhDs, 146 devote at least part of their research. 135 hold PhDs. So here we go. So here's the professors. So among professors, you either have a PhD or you do not have a PhD. So you're one of these. And now 114 of the PhD, so given the PhD, 114 do research. And then given the PhD, 21 then would not do research. And then if you keep reading on, let's see, where did this number come from? Anyway, let's keep reading on. Maybe I forgot to put that in there. This is 32, so given you do not have a PhD, the probability that you do research is 32 out of 45. Maybe I forgot to put that in the problem, or maybe I'm just reading something wrong. Anyway, here's the chart, so you can copy this down, pause the video. This is PhD and research, PhD and not research. These all add up to 1. So here is the chart. Next, what's the probability given this chart, I guess? So given this chart, given let's see, holds a PhD and or devotes at least part of his time to research. So these people have a PhD and or research. These people have a PhD and or research, so PhD. These people have a PhD and or research. These people are not counted. So we're basically going to add up all these three right here. When you add those three up, you get 0.976. Okay, next, does not hold a PhD degree and does not devote any time of his time to research. That would just be this group right here. C, will hold a PhD degree given that he devotes part of his time to research. That's not right. I did that backwards, didn't I? Will hold a PhD given devotes part of his time to research. So given research, probability of PhD. Given research, probability of PhD. So let's work this one out. So we can use the formula to help us out. Probability and research, that would be the 0.633. The probability of just research. Now there's a couple routes to go that end in research. This route ends in research, and this route ends in research. So you have to add those together. When you work out that probability, you get 0.7808. And then lastly, will devote at least part of his time to research given that he does not hold a PhD degree. So I always put the given in first. Given that he does not hold a PhD, devote part of his time to research. That's what we're looking at right there. And in this one, we already have this in our chart. It's 32 out of 45, which is 0.711. Okay. Let's see. I think that there was a little problem here. This was 32 out of 45. So I guess this problem ended up being, given this chart, fill out the rest. I don't think I gave you the 32 out of 45 here, did I? No. Well, there it is. And then we can answer the rest from the chart. Alright, last example we're going to do for a tree diagram, and that is example 5. We reported on a new computer-based test for an ovarian cancer. Ovarian cancer afflicting only 1 in 5,000 women. Okay, so that's this right here. So women either have ovarian cancer or they do not have ovarian cancer. Now they're going to be tested. The test is highly sensitive, able to detect the presence of ovarian cancer in 99.97% of women. So, given that you have cancer, the probability of a positive test is 999. There's another 9 right there. My mistake. Of women who have the disease. However, it is unlikely to be used as a screening test in the general population because of the false negatives of 5%. So that would be this. That would be this. This is a false negative right here. So given you do not have cancer, it comes back as positive 5% of the time. Draw a tree diagram and determine the probability that a woman who tests positive, so given they are positive, actually has cancer. So that's what the question is looking at right there. So pause the video, you can copy down this tree diagram, and we'll take it from there. Alright, So there we have it. So now we're looking for the probability that they have cancer given that they tested positive. So we got to do cancer and positive divided by the probability of positive. So the probability of cancer and positive is right there. That's 0.00019994. Probability of positive, well, again, here we've got this is positive, so we got to count this, and this is positive, so we got to count that. So 0.00019994 plus 0.04999. When you work that out, you get about that. So about 0.398% of the time is the probability that you have cancer given you tested positive. Alright, so that is that. That's our homework. You have the homework here. Do a tree diagram for 5.54, and the rest should be straightforward.